All right. So we learned about cations and anions. We learned last time how certain elements on the periodic table, and we can look at the periodic table and kind of understand this a little bit. Some elements, like chlorine, want to gain an electron. They want to do chemistry, interact with other elements to gain an electron. Do you remember why chlorine would want to gain an electron?
Because it's, no, I don't.
All right.
It has to do with the charges.
Yeah, it has to do with this as well. I'm going to draw a picture. We're going to play some Pictionary here.
Okay.
Let's see if you can, if I can remind you with this, okay? So I'm drawing something here.
Oh, yeah.
What am I drawing?
You're drawing the cation.
I'm drawing argon. Argon, right?
Oh, argon. Okay.
And why am I drawing him with a crown?
Because he's the king.
He's a noble gas, right? He's a noble gas.
Noble gas. Yeah, that's.
And what makes the noble gases noble, for now at least, is the number of electrons that they have, right? 2. Helium has 2. Neon has 10. Argon has 18. Krypton has 36. Xenon has 54. Radon has 86. So if atoms can find themselves in a scenario with the same number of electrons as those noble gases, then they stabilize themselves. They attain a degree of stability. So, for chlorine to stabilize itself, what does it have to do in terms of electrons?
It needs what?
It has 17, right? And it would like to have 18, right?
Like to have 18.
Yeah, so it wants to gain 1 electron, right?
Okay.
Yeah, so looking at chlorine has 17. Now remember, that's 17 up there. It's the number of protons, but it's also the number of electrons. So we can use that number to identify the number of electrons that an atom of whatever element will have. So chlorine has 17 protons and 17 electrons. And if it gains 1 more, then it gets to be like the mighty proud argon, right? It gets to have a noble gas electron configuration. And that's the phrase we use, noble gas electron configuration. Kind of a uncomfortable phrase initially, but we'll get used to it. But it's essentially saying if you have the same number of electrons as noble gases do, you stabilize yourself as an element. All right? So let's look at another example here. Let's look at the other side of the periodic table. Let's look at sodium, which is element 11. Element 11. All right, if we look at sodium, element 11, and say, what does it have to do to attain a noble gas electron configuration?
Okay, it needs to lose an electron.
Very good. Sodium needs to lose an electron. Very good. So what we're kind of seeing here is we're learning that based on where the element is on the periodic table, it tells us information about how it likes to do its chemistry, right? So let's look at oxygen, element number 8. What kind of chemistry do you think oxygen likes to do in terms of electrons? Does it want to gain electrons or lose electrons?
It would, those are the only 2 options?
Yeah, oxygen can either gain electrons or lose electrons.
Okay.
And whatever it does, it wants to get a noble gas electron configuration.
Oh, okay. So then it wants to gain an electron.
How many does it want to gain?
2.
2. That's right. It'll be easier for oxygen to gain those 2 as opposed to losing 1, 2, 3, 4, 5, 6. Right? So gaining those 2 electrons, and that's what we see. Oxygen in its compounds, in its ionic compounds, always has a -2 charge. All right? Now remember, when an element gains 2 electrons, sometimes we get tempted to think, oh, the element gained 2 electrons? Well then, if it gained 2, that's 2 positive, right? Positive 2, gaining 2, plus 2. No, that's not how it works, right? The charge that goes there is telling us the electron, or the balance between the protons and the electrons. And the balance, if oxygen has gained 2 electrons, now it has 2 extra negative charges. And that's where the -2 sign comes from. It's not subtracting 2 protons or subtracting 2 electrons. It's the resulting charge when 2 more electrons are added. All right, does that make sense?
Yes.
So let's look at the periodic table and do one more example. Nitrogen. How would it like to either gain or lose electrons to attain a noble gas electron configuration?
3.
Yeah. What 3 what? What is it going to want to do with 3?
Oh, 3 electrons. It wants to gain 3.
It wants to gain 3 electrons. Very good. So that would give it an N3 minus charge, -3 charge, right? Very good. Let's look at element 38, strontium. Strontium, element 38. What is it going to want to do to stabilize itself? We need to find the nearest noble gas, right?
Right. And so that's krypton.
Yeah. So what can it do to attain a noble gas electron configuration similar to krypton?
Lose
That's right.
2 electrons.
Very good. Lose 2 electrons.
And then, so when losing the 2 electrons, it will have a positive charge.
A positive 2 charge. Very good. Excellent. Now, that also puts us in a position where if we're provided ions, for example, if somebody says, this is an iron +3 ion, and this is an oxygen 2- ion. If we're provided these ions, we're now in a position to predict how these 2 ions will come together to form a compound. All right? Now, how did iron get that +3 charge?
It gave up 3 electrons.
That's right. It gave up 3 electrons. Where did it give them to?
Let's see. Think of it. Let me look on the chart.
Well, you don't have to look on the chart. All you have to do is see over here to the oxygen, right? The oxygen has the negative charge, right?
Okay.
So it's giving, that's what happens in these reactions. One element is giving electrons to the other. But the problem here is that oxygen only gains how many electrons?
2.
2. So if iron gave up 3 and oxygen gained 2, that third electron, where does it go? Well, it has to go to an additional oxygen atom. So our chemistry that's occurring, we have a iron +3 charge, oxygen with a -2, but we need to have another oxygen around to take more electrons because iron gave up 3 and the oxygen only took 2. But now we have the iron giving up 3 and the oxygen needing 4 electrons. So we need to have another iron atom that would give up 3 more electrons. Now there's a total of how many electrons given up?
6.
6. And a total of how many taken?
4.
4. So we need one more, right? We need another oxygen. Excellent.
Okay.
So what that puts us in a position where 6 electrons were given up and 6 electrons were accepted. And so I can see that the result of iron +3 and an oxygen 2- is going to be a compound that has Fe2O3.
I see.
So that's how we can predict the kind of ionic compound. And again, this is an ionic compound. Now let's remind ourselves what the term ionic compound means. We said we could recognize an ionic compound because it contained a metal, right? But a more refined definition of an ionic compound we decided was it's a compound that is made of ions, right? Which is a boring name, boring title. But we have to remember that because, well, we'll see in the future why it's important, but we also want to know where the term ionic compound comes from. Now, and another reminder, I think we already know, but an ion is an atom that has an imbalance between the number of protons and electrons. It's an atom that's either gained electrons or lost electrons. I'd like to point out one other little trick here. If I have the iron +3 and I'm wondering how it combines with the oxygen -2, I can just kind of draw arrows like this, and I'll see that the two irons and 3 oxygens will balance this. That's just kind of an easy way to find the least common multiple for the +3 and the -2. All right? And we'll introduce that again also later on.
Okay.
Okay. So, how does calcium, here's a little quiz, how does calcium go from Ca to Ca+2?
It's losing 2 electrons.
Very good. It loses 2 electrons. How does N3 get formed from nitrogen? How does nitrogen go to N3-?
It's gaining 3 electrons.
Excellent job. Excellent job. It's gaining 3 electrons. We never lose or gain protons in chemistry class, right? We're losing or gaining electrons. People always ask me, why did you get interested in chemistry? It's such a hard subject, blah, blah, blah. Why did you get interested in it? Because this is the most fundamental way that nature works on a very large scale that we can mimic and manipulate on a very large scale. It's true that atoms can actually lose protons or gain protons. And you can get different atoms. So, in a way, the word chemistry, alchemy, came from this idea that you could change lead into gold because the kings wanted gold, they didn't want the lead, right? Is it possible? Yeah. Somewhere out there you can actually add protons to elements and get different elements, but not on a significant level, right? So is it happening enough that it influences our life and our world and our environment? Yeah, it is. Carbon-14 dating, right? All the elements around us are always decaying. We have nuclear bombs nowadays, right? So things are happening that include the increasing or decreasing the number of protons in an atom, but it's not happening on a large enough scale that we can manipulate it as much as we can manipulate the chemistry, which is the changing of the number of electrons on our elements. Okay? All right, so here is the reaction that we introduced last time, and we can go over it again. Sodium reacting with chlorine. Sodium was sad because it needed to get rid of an electron. Chlorine was sad because it needed to gain 1 electron. The result was a transfer of electron from sodium to chlorine, and the resulting material, sodium chloride, is the combination of these 2 ions, the sodium cation and the chloride, And notice how we change it from chlorine, this is a chlorine atom, to a chloride ion. All right, so that's kind of a little tidbit that we'll catch on to later on. Sodium ions and chloride ions come together to form sodium chloride. And sodium chloride, you're familiar with that. It's salt. Here's a video of us taking a little piece of sodium here, putting it in a flask of chlorine glass, which is green. All right, we're going to use this rod to make the sodium get off of the glass tubing. We have some sand on the bottom to prevent the glass from cracking when the reaction occurs. Nothing happens initially because there's what's called an activation energy, and we'll talk about that in the future as well. But we put a little drop of water in there to kind of help the sodium react a little bit. And when it gets hot and starts reacting, then it can encompass the chlorine, give its electrons to the chlorine, and the result is a hazy white substance floating around, a hazy white smoke. It's a solid in particulate form, and that is our sodium chloride. All right? Salt is what people call sodium chloride, but the chemistry world kind of did the rest of the world a disservice when they called sodium chloride salt. It's not just the salt, it's just a salt. It's a salt, because a salt is really any ionic compound. The combination of any metal with a nonmetal is called a salt. So you go to the restaurant, you ask for salt, they don't say, what kind of salt, right? Right? We all know that salt in the world means sodium chloride. Well, it means what they sell as salt. Because really it has potassium chloride in it, it has sodium chloride in it, it has other compounds as well. It even has a little bit of glass, silicon oxide, to prevent the caking, right? And if you're in Hawaii, you have to help the anti-caking agent by adding rice to your salt, right? Another hydroscopic material to pull the moisture away, or otherwise it just gets clogged and it won't come out, right? But the take-home message, salt in chemistry class refers to any ionic compound. All right, so if we take a salt and put it into water, it makes the water conductive. Or if you take a salt and melt it and make it molten salt, it will also be conductive. And these are evidences, experimental evidences for ions. Now, sometimes people get confused and think, oh, the salt is making electricity because the light is on. So we have to kind of clearly explain what this means when we're talking about making a solution conductive. We're going to play a little, what's it called, Pictionary again. I'm going to draw something. As soon as you know what it is, you tell me, okay? Here we go. I'm drawing something here. Looks like this.
A battery?
Yeah, that's right. It's a 9-volt battery. Very good. So I have this battery, and I have, here's something else.
Light bulb?
Light bulb. Very good. If I take a wire and connect it to this side of the light bulb, and then take another wire and connect it to the bottom here, then if the battery has enough energy, it will light up the light bulb, right? The electricity is coming from the reaction that's occurring in the battery. If I do the same thing but this time I don't let the wires touch, am I going to get any light?
No.
No. The wire has to touch, because what's happening in this battery is a chemical reaction where it's trying to push electrons through the light bulb and then come to the other side. If it can't get to the other side, then the electricity can't flow. Here's another something I'm going to draw here. See if you can tell me what I'm drawing here.
Oh, okay.
What is it?
The outlet.
Yeah, it's an outlet. Kind of a poor drawing there. It looks like ghosts or something. But this is an outlet. And you remember in the olden days, the outlets used to just look like this, right? Didn't have the ground, the safety. Well, same idea. Electricity is coming in one and going and wants to go back in the other, but you need to provide a circuit for that to occur. So if we don't have the leads touching, then the light bulb can't light. If I take maybe a piece of metal and I touch that metal between those two leads, then I'll get the light bulb to light up, right? Or touch, because metal is conductive, right? If I dip these two leads into a solution of water, H2O, I still won't get the light bulb to light up. Now, you don't want to try this at home, because if you take tap water and you rig up some sort of system like this, it'll light up. It'll light up because tap water is actually salt water. It has salt in it. Not necessarily only sodium chloride. It has other salts, nitrates, phosphates. It has calcium, magnesium ions with other anions. So there is a significant amount of salt which will allow it to be conductive. But if you have what we call deionized water, just water, you will not get a light bulb to light up. Now, if I take a salt, now what does a salt mean in chemistry?
In chemistry, any
What kind of compound is it?
said ionic.
Ionic, that's right. Anionic compound. A compound that contains ions. If we take that salt, put it into the water, then we will get our light bulb to light up, right? The salt provides conductivity to the water, all right? So when we talk about this, and this comes up every once in a while, the conductivity of a solution, what we're referring to is a setup like this, where the salt or the molten salt isn't providing electricity, it's just allowing conductivity. The negative and the positive signs here are showing that we're providing electricity somehow. So this is evidence for salt or for ions. Those ions allow electrons to transfer back and forth. A salt solution makes the solution conductive. A molten sodium chloride solution also results in the light bulb lighting up, or a conductive pathway for electricity. All right, molecular compounds like water. If I put sugar in the water, it won't light up, right? Those molecular compounds will dissolve in water. You know, we know that sugar dissolves in water, but it doesn't result in ions. Therefore, it doesn't give conductivity to the solution. All right, remember this game? We played this game not too long ago. Can you see it okay?
Yeah.
All right, so let's give it a shot. Let's see here. This is now cobalt 60, but it has a +3 charge. A +3 charge.
Okay.
Do you know how many protons, using your periodic table? Can you tell me how many protons are in cobalt 60?
Yeah, let me just get to it.
Cobalt is right here on the periodic table.
Okay, I'm looking for your arrow. Oh, okay. Yeah, okay. So then it's
How many protons?
23
27, right? 27 protons?
or 27. Yeah,
27,
27.
yeah. 27 protons. Very good. How about neutrons? How would you decide how many neutrons are on this atom of cobalt? Remember, we call it cobalt 60 because that 60 is the mass, right? So now you can use your calculator.
Okay. Okay, can we stop for just a second?
Okay, so if we take the 60, cobalt 60, and remember that 60 is the mass of the protons and neutrons, so we subtract the 27 and that gives us the 33 neutrons. Now here's the part that's a little bit new. Electrons. Before, if there was no charge, we would say the number of protons is the same as the electrons. But can you see that there's a charge on that atom?
Yes.
All right. So how does that plus 3 change the number of electrons? How many electrons should there be on this species?
24.
24. Very good. 24 electrons. And that's the hard part. So excellent job. All right, let's try the next one. Here's bromine 81. Bromine 81. Now, in terms of elements, bromine is off to the right. It's a halogen, second to the right column. How many protons in bromine?
35.
35. Excellent. Now, how many neutrons?
46.
46. 46 neutrons. Very good. Now, how about electrons?
35.
35. The same as protons? Oh,
Yes.
maybe you can't see. There's a negative charge
Is there
on
a charge?
bromine. Yeah, it's a negative.
Oh, no, I
Small.
can't. I couldn't see the negative charge. Okay, so that would be 36.
36 electrons. Very good. Very good. All right. Now, the symbol off to the left here for this last scenario. 29 protons.
Okay, copper.
All right. 36 neutrons. What does that tell us? We're going to call it copper what? Are we going to call it?
Copper. Yeah, copper. 60. What? 65.
Very good. Copper 65. Does it have a charge?
It has a charge.
It does?
Yeah.
What's the charge on it?
The charge would be a positive 2.
Very good. Copper 65 with a positive 2 charge. Excellent. Well done. Okay. So, we already talked about this slide, so we're not going to spend a lot of time here. We talked about it because our conversation earlier was talking about how based on the location of an element on the periodic table, you can determine whether it wants to lose electrons in an ionic compound or gain electrons in an ionic compound, right? So
Right.
the alkali metals, lithium, sodium, potassium, rubidium, cesium, right? They all want to lose electrons because they're over there on the left. The alkaline earth, that's the second column, the alkaline earth, they all want to lose 2 electrons because they're all 2 columns away from the noble gases. The halogens, that's the fluorine, chlorine, bromine, the column, the second to the right, all the way over to the right, the second to the right, fluorine, chlorine, bromine, iodine, they all want to gain 1 electron, right? Oxygen,
Right.
sulfur, selenium, that's number 8, number 16, number 34, they all want to gain 2 electrons. So we've already talked about this, how based on their location on the periodic table, you can tell what kind of ion they want to form. So calcium wants to form a +2 charge because it's 2 elements away from a noble gas. Sodium wants to form a +1 charge. Nitrogen, do you remember? Can you look at the periodic table and tell me what kind of a charge nitrogen would like to form?
Yeah, it wants to form 3 neon. It wants to
gain 3 electrons. What kind of a
I'm
charge would that
sorry.
be?
Yes. It would be a negative charge.
-3. Very good. -3. And oxygen? It's right by
Oxygen would
nitrogen.
be a -2 charge.
-2. Fabulous. All right. So, now we're going to learn how to write chemical formulas for these ionic compounds. All right? And there's nothing magic about it. It's pretty straightforward. Essentially, the metal goes first,
Okay.
and then the non-metal. And the balance, or the charges of the metal and the non-metal need to balance. Like we just took that iron +3 ion and that oxygen 2- ion. We found out how many of each there was necessary to balance it, right? You need to do that, okay? So let's look at some examples. If I have aluminum ions, aluminum with a +3 charge, and why don't you find aluminum on the periodic table? Can you find it? It's number 13.
Okay.
See how it, to attain a noble gas electron configuration, what does it have to do?
It needs 5. 5 negative charge.
Yeah, that's a big negative charge. Is there any other way it can attain a noble gas electron configuration?
Well, that is big. Yeah. Okay. It could have a 2 positive charge.
2 positive or 3?
I'm sorry. Yeah, 3 positive
3.
charge.
3. That's right. And
Right.
that's what aluminum does. Aluminum forms a +3 charge when it forms its compounds. So, we can see that, hey, it could gain those 5 electrons and become like argon, but it can stabilize itself easier by just losing the 3. All right?
Okay.
So, aluminum with a +3 charge, if it's going to come together with an oxygen with a -2 charge, right? What is the
Okay.
resulting compound that's going to form between these 2 ions? What is the chemical formula going to be?
It's going to be aluminum oxide. Right?
Aluminum oxide.
And that would be, we could just, well, it's going to have, to balance, we would have to balance it.
Uh-huh. How many
And
aluminums?
so it would be Al2 and O3.
Very good. And there's our little crisscross rule we talked about. Al2O3. Excellent job. Okay. Now, the next one. Magnesium and oxygen, their ions coming together. What's the resulting compound going to be?
Okay, so magnesium oxide.
Magnesium oxide, good.
And it will be no charge.
No charge? Well, yes, that's right. There's not going to be any charge on it. But what's the ratio?
Okay, so I guess it'd be Mg2 and O2.
Okay.
Will we still write it like that?
No. I think this is
Okay.
what you meant when you said no charge. You meant no, just 1-to-1 ratio.
That's right.
Right? That's right.
Yeah.
So that's good. That's good.
Okay, but you mentioned still has a charge, so
Well,
I'm still not grasping that apparently. So
it doesn't have a charge. The ionic compound as it's written, there's no charge on it, right? There's no charge up
Right.
here on the MgO or the Al2O3. The ions themselves
I see.
kind
Right.
of have
I'm
those
mixing.
charges. What's that?
Okay, so we're talking ions where I was talking a charge, right?
Well, no, that's the same thing. That the charge, that the ion, I don't know, maybe it's different, but the ions have the charge, right? But once they come together, then there's no charge on the resulting compound, right?
Okay. Right.
Now, we begin to introduce what we call polyatomic ions. So some ions can form by bringing a lot of different atoms together, and the resulting cluster can have a charge. So for example, 1 nitrogen and 4 hydrogens, they will gather in such a way that they'll result in an ionic species with a positive charge, a cationic species. And this is called the ammonium ion. Ammonium ion. This to the right of it is another polyatomic, meaning many atom ion, polyatomic ion. This is phosphorus combining with 4 oxygens, and it comes together to form the phosphate ion. Phosphate ion. And the phosphate ion has a -3 charge on it. All right?
Okay.
So this is new information, right? A new set of what we call, again, polyatomic ions. And there's a list of these polyatomic ions on the back of your periodic table. All right? It looks something like this.
Yes.
You see that list okay?
Yes.
Good. So the list of polyatomic ions can be used like the periodic table, meaning that when we see a polyatomic ion and we don't know what it is, we turn our periodic table over, we find the name of the periodic, the polyatomic ion. And finding that name is the learning. That's how you begin to recognize polyatomic ions. If you just see a polyatomic ion and you say, oh, it's a polyatomic ion, I can't remember what his name is, but I'm pressing forward, I'm out of time, right? Well, you're going to miss the opportunity to learn. So we use this sheet, we turn it over whenever we need to remember the name of a polyatomic ion. And after we do that multiple times, eventually the polyatomic ion becomes a friend of ours, and we remember it always, right? We remember it. So that's our list of polyatomic ions. And now we kind of introduce why we wanted to change the definition of an ionic compound. Because you see here that these ions don't contain any metals. And yet they're going to come together to form an ionic compound. So almost, most ionic compounds contain metals. And if the compound contains a metal, it's an ionic compound. But there are some ionic compounds out there that don't contain metals because they can contain this ammonium ion. Ammonium ion. If we look back at our periodic tables, our polyatomic ion list, look back at our polyatomic, where is it at? Here it is. Back to our polyatomic ion list, there's really only one positive polyatomic ion, and it's this ammonium ion. The hydronium ion, it doesn't form salts, and we'll talk about that one in the future. But the ammonium ion can form salts, again, ionic compounds. So, let's see. Can you tell me the chemical formula then for ammonium phosphate? What ratio are they going to come together in? How many ammonium ions do I need?
3.
3. That's right. I need 3 ammonium ions. And so I use those parentheses around the polyatomic ion, put a 3 there, and then 1 of the phosphate ions. So that's ammonium phosphate. Okay, very good. Now, I'm going to show you how ionic compounds. Have I showed you this video before? I think I showed you it already. I'm not positive. But this is, I'm not a cation. So this is the this is how ionic compounds are at an atomic level.
By attractive forces between.
You have these negatively charged ions, and these are chloride ions, and you have positively charged ions these are sodium ions. So we have these ions coming together in what's called a three-dimensional lattice. A three-dimensional lattice. All ionic compounds reside as these three-dimensional lattices. Not like molecules. Molecules are individual packets that are separate from each other. But ionic compounds come together in these three-dimensional lattices. And the reason why we bring that up at this point is because for the MgO, the magnesium oxide, we didn't put Mg2O2 because all we're saying with the formula of the ionic compound is that that is the ratio of the different ions, right? 1 magnesium for 1 oxygen, 2 aluminum for 3 oxygens, 3 ammonium for 1 phosphate, all right? We're not saying that there's only 1 sodium and 1 chloride going around together because they occur in three-dimensional lattices like this. When you put something like sodium chloride into water, the sodium chloride dissolves. Also what we call dissociates, but we'll talk about that word later. The dissolving process is where the water molecules surround the individual ions and pull them off into solution. So here the water molecules are surrounding an ion of sodium, a sodium ion, and they're going to pull it away and entertain it as an individual ion. And it's these individual ions that result in the conductivity of water. All right. Very good. So, the take-home message, why did we look at that video? Is that when we see the chemical formula for an ionic compound, it's just telling us the number of that given atom in the ion. Okay. Okay, next one here. Potassium and oxygen. Potassium and oxygen. Which of the following is the correct formula for the formula unit composed of potassium and oxygen? How do we do this one? Can you look at the periodic table to figure this one out?
Potassium, oxygen. Okay. Can you pause for a minute?
Yeah. Okay, so let's talk through this one. We need to find potassium and oxygen. So if we search our periodic table, can you find potassium?
Yeah.
Okay.
19.
Potassium, number 19 there. And we can find oxygen, number 8, right?
Right.
So potassium, what does it need to do when it forms an ionic compound? To become like a noble gas, what does it need to do?
Yeah, it needs to gain.
19, it's going to go to what?
Oh, I'm to 18. I'm sorry.
18.
It
needs to lose an electron, right?
Right.
Okay, good. So it needs to lose an electron. So potassium is going to form, and let's grab a piece of paper here so we can look at this a little bit better. Potassium is going to form a K. Potassium needs to lose an electron, needs to form a positive ion, right?
Right.
Now, what does oxygen going to do when it forms an ionic compound?
So it's going to gain.
How many?
And form 2. It's going to form a negative
That's right.
2. Yeah.
Very good. Now,
Negative.
when these come together, what is the resulting compound going to be?
it's going to be a KO negative
So is
negative
it
charge.
KO, or is it KO2 or K2O? Remember how we can use our
Yes.
crisscross rule?
Oh, that's right. That's right. So, yeah, K2, number C, yeah.
Very good. Excellent job. And
So
again,
the question,
yeah, go ahead.
okay.
Go ahead. What were you going to say?
So, well, I get the crisscross. It's the, if you could then talk about the charges, right?
All right, yeah. So again, if we have information saying that our compound is going to be made of potassium, we can look at the potassium atom, see that it's 19 protons and electrons, and see that its nearest noble gas is argon. It has 18 electrons. So potassium needs to lose an electron to attain a noble gas electron configuration and become like argon. Okay? And oxygen needs to gain 2 electrons because it has 8. It needs to gain 2 electrons to find or to become like neon to attain a noble gas electron configuration. And once we see that potassium needs to form a positive ion, and oxygen, a positive 1 ion, and oxygen needs to form a negative 2 ion, then we can realize, and you can use the crisscross rule if you like, but we can also just realize that if this took 2 electrons, that means it's going to require 2 of these potassiums that are going to lose an electron each. So that's how we know that it's going to be a K2O.
Okay, and at that point, I guess where I'm a little confused, right? Going to the left, we see potassium, right?
Mm-hmm.
With a positive charge. We understand the charges. When they're combined, we lose, or at least in my mind, I lose the charge. Right?
Well,
I can't tell.
there will be no.
Tell the
there-
charge from the K2O.
Yes,
right?
that's right. You can't. Well, you can't tell simply by looking at that compound. K2O
Right.
doesn't have a charge on it anymore because there is 2 of these Ks. 2. I should put a 2 here, right? There were 2 potassium ions that came together with 1 oxygen ion. But because those charges canceled out, the result is no charge on that compound.
Okay.
So if there was a charge, it would show up right there, right? But there's no charge.
Then, yeah. Okay.
Okay, very good.
That's right. Okay.
Now, we can use the periodic table to kind of predict the kind of charge atoms like sodium, potassium, calcium, strontium, these first 2 columns, and also to predict the charge on the nonmetals. However, if we want to start predicting charges for our transition metals, like manganese, iron, nickel, copper, it becomes more tricky. And we won't have a conversation about how we can predict that charge for quite a while. So when we see elements in the transition metals, within the transition metals, anything in this blue or this inner transition metal group, if we see elements like that in ionic compounds, we have to recognize that those elements might have various, what we call charge states, various charge states. So for example, iron, it can form a +2 charge or it can form a +3 charge. Copper, a +1 charge or a +2 charge. Tin, +2 or tin +4. Right? So you have a variety of what we call transition metals, right? We call them transition metals because we said that this section on our periodic table was the transition metals. And also some of these orange ones here, which are called post-transition metals. They have multiple possible charge states. All right? So we're not going to be asked to be able to predict what the charge state will be at this point, but we do want to know, for a rule for now, is if it's a transition metal or a post-transition metal, the orange here or the blue, that it's able to have multiple charge states, Okay,
Okay.
very good. Do you have a question?
So the transition metals are, can you point on the periodic table again?
Yeah, these blue ones right here are our transition metals.
Okay, and then the post is the orange.
The little orange triangle right to the right of them, yeah.
Okay.
So here's a question. Which of the following is a correct formula for the formula unit composed of iron +3 ion and sulfide ions? Sulfide ions.
Okay.
Let's look at our periodic table here and see where sulfide ions are. There's sulfur, right? So what's the charge going to be on a sulfide ion?
So it's going to be a -2 charge?
That's right, -2 charge. So the question is asking, what's the resulting compound when we combine? What are we combining here? An iron +3 charge and a sulfur 2- charge. Excellent. So what is the resulting compound going to be? Fe.
C.
What?
Fe2
Uh-huh.
and S3.
3. Very good. C. That's what you said, right?
Yeah.
All right. Excellent. So that time we weren't told that we're combining iron with sulfide. We were told a specific ion because iron is in this blue space. And what do we call this blue area?
The transition.
Transition metals. So we remember that iron can have multiple charge states. All right. Very good. So our list of polyatomic ions. Here it is on the back of our periodic table as well. And it's going to be helpful for us to look for those whenever they are introduced to us. Okay? I should note that this is not an exhaustive list. There are many other, and possibly, well, hundreds other kinds of ions that can exist as polyatomic ions. And sometimes we'll be tested on them, not because they're trying to be mean, but because they're trying to test our understanding of how polyatomic ions work and how ionic compounds that contain polyatomic ions work. So here's an example. The platinate ion forms a compound with rubidium as follows. Rubidium-3 platinate. What is the formula for iron 3 or iron 3 platinate? Iron 3 platinate. Now the 3, when it's written like this, the 3, that's telling us that the iron has a +3 charge in this compound, or that this compound is made from ions with iron +3. Rubidium. Rubidium. Rubidium is element 37. Can you find rubidium on the periodic table?
Okay.
What kind of a charge does rubidium want to form in the polyatomic when it forms an ionic compound?
It wants to wants to give up one electron,
And what kind of an ion is that going to give it? Result in?
and that would give it a positive charge.
A positive charge.
Positive one. Yeah.
That's right, positive 1 charge. So we see that this compound, which we've never heard of before, rubidium platinate, apparently the rubidium must be a +1 charge. So what does that tell us about the PTO4? What's the charge on the PTO4 ion?
Okay.
Can you do the reverse crisscross here with this compound? RB3 PTO4?
PTO4.
What is the charge on the PTO4 ion?
Okay, and we're going to crisscross. Oh, I see.
The rubidium has a what? A +1. We already looked that up.
Right.
And if it says we need 3 rubidium for every 1 platinate, the platinate must be a what?
Minus.
A -3 charge, right?
Right.
Can you see that? Because we were told that we needed 3 rubidiums, and because rubidium is at a place on the periodic table where it always has a +1 charge, anything in this first column will have a +1.
Okay.
Therefore, that must mean the platinate is a -3 charge.
Oh, okay.
So if the platinate is a -3 charge, then we can answer the rest of the question. How is it going to want to combine with an iron +3 charge?
So it's going to oh, I get it. Okay.
What's our answer? What do you think? Is it going to be 3 irons for every 1 PTO4, 2 irons for every 1 PTO4, or 1 iron for every 1 PTO4?
It's going to be 1 iron.
That's right, because it has a +3 here, and that has a -3 there. Very good. So it's just going to be a 1-to-1 ratio for the PTO4.
Okay.
Okay, very good. I think that's a good place to stop. Good job. Good work. A lot of hard stuff, but you're doing good.